All right, so now we're going to look into some uses, some benefits, and risks of nuclear chemistry. So we already looked at neutron capture, and this is towards fission, where the neutron is shot at uranium to make it too big to split in half. Because remember, fission is division. And when it does that, it releases 2 to 3 neutrons also, which then bombard another one, causes them to expand and then divide, shooting off 2 to 3 more. All right, so this is just real quick the equation of the neutron capture by uranium. It gets too big, then it splits into 2 different particles, 2 different elements, xenon and strontium, and then it releases 2 to 3 neutrons. So this is the induced fission. This is made in nuclear plants, where they throw the neutron at the uranium, which causes the uranium to get big. Because look, it's 92, it's way too big, it's going to decrease somehow. How is it going to decrease? It's going to split in half. It's going to divide. And then it's going to shoot off, like I said, 2 to 3, and the ones are in really weird spots, so sorry about that. Here's the other way it could happen. This is why I said 2 to 3. There's 2, there's 3. So another way that it could split is this way, where again, it's bombarded with a neutron, and it increases, and then it splits into krypton and barium with 3 neutrons left over. Okay, so this is what's going on in the nuclear plants. In a nuclear plant, this is just a simplified version of it, where you have a containment shell with the reactor, and inside the reactor, you have the fuel rods and the control rods, along with water or a moderator. And this is going in a circle. Remember, when this is going on, it's getting really, really hot. It's heating up that water, which then goes through here and ends up heating up this water, this bunch of water from a different source. And then it goes around again. And there is a pump to keep it going in a cycle. Because you don't want all the hot water staying over here. You want it to kind of cool down and moderate. So it's getting moved throughout. And then over here, we have this huge steam engine where steam is made right here because that heats up the water here. The steam pushes up and goes into a steam turbine, moving and creating electricity, which then goes, it doesn't show here, but it goes off to a generator. And then as that steam comes out the turbine, it is brought next to a condenser. So they form a condenser using water from a large source that's pumped up in here, which this is cool water hitting steam, which condenses, causing it to turn back into droplets in water, which is then pumped right back around to keep going around in a circle and a circle and a circle, which is why it is 365 days worth of energy. It doesn't have to stop. And this is just showing it again. Like I said, here's another way it works, where you have that water I was talking about before. It's all in here, and then you have another one right here, the condenser. So you have this water in the moderator, where it goes from the moderator to the turbines. So here it goes, gets heated up, steam pushes through, goes through the steam turbine, creating electricity, which goes to the generator. The generator stores that energy and releases it into the electrical wires and whatnot to our houses and schools and whatnot. All right. So in the reactor, we have reactor core, or the fuel rods, the fuel elements. What this is a fissionable uranium-235. This means something, the element that can, if it gets too big, will divide. So this uranium is enriched to about 3% of U-235. I know it doesn't sound like a lot, but we don't need a whole bunch. And then it's used to form uranium oxide pellets. So they take the uranium and they chemically combine it with oxygen to form a solid pellet, which these pellets are then put into a zirconium or stainless steel tube forming a huge long tube, and you can see it right here, the fuel rod. These reactors must be stopped periodically so that the fuel can be replaced or reprocessed. I vote for reprocess, but not all the time does that happen. So in the core, we have spent fuel rods. That's when they take them out. These are kept at reactor sites because they are radioactive. They have to be placed in special containment. So these control rods, remember me talking about those control rods? What they are rods composed of materials such as cadmium or boron, which control the fission by absorbing neutrons. Because remember what I said, those neutrons, once you shoot one, it can produce 2 to 3 more, which can hit and produce, it reproduces like bunny rabbits. And we don't want that much because that's a lot of energy. Not that we don't want a lot of energy, but we don't want all the water to automatically turn to steam, which then could lead to a meltdown. We don't want that. Okay, so on top of the control rods, which you'll notice these ones are not graphite or graphene, which would be really, really, really bad. And we'll discuss that and figure out why in a little while. All right, so then you have a moderator. So a moderator is a cooling liquid. It's either water or liquid sodium. These moderators slow down the neutrons so that they can be captured more readily by the fuel. You don't want them going around kind of like Alvin and the Chipmunk when they have lattes. They went like zooming all over the room. You don't want that. You kind of want to slow them down and have them go where they need to go instead of like everywhere. Okay, so cooling liquid is circulated through the core to carry off heat generated by the nuclear fission. This cooling liquid and moderator could be the same substance. So you could use that water. We saw that in one of them where it cools it, and as it's cooling, it heats up and steams and then comes back down and goes in a circle. Steam is used to drive a turbine connected to an electrical generator. However, steam must be condensed, so additional cooling liquid is required. Generally given it's gotten from big bodies of water. That's really why you will find that most, if not all, reactor sites are next to big bodies of water. And then we have that confinement shell. So if you remember back when we were talking about the types of radiation, we were talking what can block it. And one of the things that can block gamma rays is lead and concrete. So these confinement shells are concrete shells to shield people around from ray particles that may have escaped. And here is looking at a map with all of the operating nuclear reactors in the United States. You'll see this is as of August 2019. There's quite a few of them. I'm happy to see that. I really like it. As I talked to you guys earlier, they're looking to make micro reactors so that they can place them near cities. So say we could have one out by the lake and it could fuel Syracuse, which would be really, really cool. And if you look at Illinois. That is kind of cool. There's so many there. All right. So what I was saying earlier is the 2.4 neutrons are produced by fission of uranium-235. Why I say 2.4 is it's kind of like the average. And there's more 2s than 3s produced. What I mean by 2 is sometimes you have 2 produced, sometimes you have 3 produced. So the average is about 2.4. In order for a fission chain reaction to occur, a minimum mass of material must be present. It has to reach a critical mass. With the minimum present, only one neutron is effective in producing another fission. So you only need one. The number of fission and energy release quickly escalates exponentially if left unchecked. That's like the bunny rabbits going nuts, only with radioactive particles, which is not good. And you'll see critical mass chain reaction stops. And supercritical mass chain reaction accelerates. So you don't want supercritical, you want critical. All right. And what would happen if, say, it's unchecked? Well, you can see this is an unchecked version of nuclear fission. It's one that we don't like. It's not cool. So you have subcritical U-235, which is aimed at a target, or is the target. You've got the bomb casing, a gun barrel, for lack of a better word, and then subcritical U-235 wedge. So this wedge is going to be slammed up against that, causing an unstopped, unchecked nuclear fission reaction. So to trigger the fission reaction, two subcritical masses are slammed together using a chemical explosive. Two combined masses are supercritical, which rapidly leads to uncontrolled nuclear explosion. Not cool. All right, so if you guys have any questions, please feel free to let me know. Besides that, I hope you guys have a great day.